Good afternoon for everyone, wherever you're in the world. So today we're going to go over some of the most exciting machine learning models that has revolutionized, I would say, the computer vision um, uh, algorithms in the last 4 to 5 years. We'll go through some of the basic scenarios and we'll go over some of the DL, deep learning architectures as we're at it. And then we'll go into some of the details of P3 instances, which will also have some of the new instance types that just came online called the P3DN. And finally, we'll have some deep learning resources for you to look at. I'm especially excited about a new book that we have just published for you to start learning about deep learning, especially in the field of computer vision as well as natural language processing. So first of all, let me put deep learning into the right context for everyone. So AI has been around for many years, and we've been applying that since the 1940s. And Amazon is no stranger to that. We've been applying machine learning to different aspects of our businesses, such as Amazon Go. If you look at our logistics, and also a lot of other a lot of aspects of our businesses. And then machine learning is something that came along in the 1960s and 50s, where people are starting to use these algorithms or conventional algorithms to look at and actually build models that can solve real world problems. And finally, there's deep learning, which is a small subset of the general machine learning field. What's really exciting about the machine learning field is that if you look at the traditional methods such as support vector machines, medium neural net, random forest, a lot of these so-called models have really done very well for people in the past. But what has really happened is the deep learning neural net has surpassed human performance for a lot of tasks, including machine learning, especially in the field of machine vision. So one of the data sets that we have been looking at is something called ImageNet. That was developed by a group of researchers in about 6 years ago. Essentially, it had about 14 million images that allowed people to had various people tag these images as they were being used to train these machine learning models. So as we looked at these traditional methods versus deep learning models, we suddenly realized that by increasing the amount of data by an order of magnitude, we're suddenly able to have these deep learning models perform far better than humans can possibly do. What we're going to do today is to go over some of the deep learning architectures for machine vision, namely the convolutional neural net. We'll explain how it works. Then we'll also look at some of the scenarios, such as image classification, object detection, image segmentation, and visual search. And finally, we'll look at a very interesting new development in deep learning and machine vision. Is something called the GAN networks. So we're able to use that to generate very realistic items based on data sets that we have. So the first thing I'd like to cover is convolutional neural net and how it works. As many of you know, that machine vision is one of the field that has essentially been the talks of how deep learning has excelled and exceeded human performances. And if you look at how convolutional neural networks is in a more visual fashion, the way I would explain it is to using a set of filters to look at an image and be able to reveal the edges and different bright or light spots of an image, and be able to figure out what are the different levels of abstractions as we go up the stack. So as we add more layers to the neural net, we're able to abstract these images from simple edges to perhaps facial content like noses and mouths, and to all the way down to items like a specific person. So using a stack of these convolutional neural nets, you're able to really go into a lot more details and build a very precise model that can distinguish different image types based on the training data that you have. So once again, in the previous slide, we mentioned that the more data you have, the better your accuracy of your model will become. So let me actually go back and do a demo first. This is actually a very simple demo that shows you how convolutional neural net works. So here I am going to this website, which you can also follow along. So the data set is something called the MNIST, or essentially, handwritten digits. So the idea is that you are building a convolutional neural net, that is able to classify what I am actually writing on the screen here. So in essence, this is probably one of the simplest models that you can build. So in this particular case, I have essentially 4 layers here. So the first layer down here is the convolutional layer. If you start looking at how it works, it's essentially showing scannings of the previous layer by applying a filter to it. And if we go to the next layer, we are actually summarizing. So for each of the adjacent pixels, we're actually summarizing that to become a smaller, I would say smaller square, but essentially it summarize the surrounding pixels into an abstract layer. As we go up the stack, we're essentially doing the same thing. So as I said previously, the convolutional neural net applies different filters to the original image, and as it goes up the stack, it performs the convolution first, which is a scanning of the original image by applying a filter to it. And then the next layer is that it summarizes the convolutional layer. And then as it goes up, it does more of the same until it's able to connect them to these so-called fully connected layers. So, and if you go up the stack even further, there is a classification layer which takes the digits that goes from 0 to 9 that gives you a classification. So in essence, I'm taking images, and as it passes through the neural net, it summarizes it and eventually comes to the conclusion of whether of which number it's actually representing. So in many ways, it's essentially a very good summarization of what these images are actually doing. So the training of these models, the way it works is that you pass a lot of these images through the neural net, and it does the forward propagation, and it will do a back propagation to weigh the neural net so that they have the proper numbers assigned to them. So at the end, in fact, you can see it from this particular pixel. So as it assigns the weight throughout the neural net, it can, as passing through multiple passes of these numerical numbers, it's able to build a system that is can classify these digits very accurately. So that's essentially how the model works. So in essence, unlike traditional machine learning models, these neural nets are able to capture much more complex, I would say complex models that's beyond just linear. So these can be very complex nonlinear models that are actually being captured by these billions and billions of neurons, and essentially be able to do things much more accurately. So in essence is that you have a very large model that is able to capture complexities that you don't normally see in a simpler model. Okay, so let me go back to the slides. So convolutional neural net is then applied to things like object detection. So as many of you have seen the revolution of self-driving vehicles. So there's a lot of interesting things that people are doing with object detection in self-driving cars. So you certainly want to have lidars that are looking at the surroundings of your as you're driving. So there are these lidars that would detect things that are how far away things are in front of you, behind you, next to you. There are also cameras all around the vehicles that are detecting objects as they pass by. So the way object detection works is that it's actually running a bounding box and running hundreds and hundreds of image classification by itself. So as you look at a scene, you are essentially trying to optimize with the right size of boxes to detect how many different images there are in the scene and what these images actually are. So there are a lot of methods that you can apply to these type of applications. Single shot detector is one of them. Of course, there are other methods that you can look into. So another more advanced way of looking at images and the scenes is something called image segmentation. So the idea is that you'll be able to find the silhouette or the boundaries of these images. So there are data sets that you use to train these models to do segmentation. Microsoft Cocoa data set is one of them. As we mentioned earlier, image classification, people used ImageNet with tagged images. So this particular data set is something called MS Cocoa, which you use to look at the boundaries of different objects. So all of these are essentially supervised learning in which you are being trained, the models are being trained through a data set that are human labeled for you. And there's usually a lot of label. So here's another data set called KITTI, which is which has images as well as LiDAR depth data, which people use to train self-driving vehicles. So there are a lot more advanced methods for people are using to train their machine learning algorithms for machine vision. So for example, there are folks that are using 2 cameras to train a self-driving car, and then you can use 1 camera to do the inference or actually figure out the depth of the vehicles in front of you or behind you. So if you think about it from humans' perspective, so we actually can perceive depth using 2 eyes, but if you block one of your eye as you're driving, you can still drive, right? So those are the kind of things that machine learning algorithms are able to do by using trained data sets. There are a lot of creative things that people are doing in the field. So another concept which I want to mention is something called visual search. So this is used by a lot of companies. So Pinterest is one of them. So they have a lot of they have invested a lot of time and effort into building a visual search engine. Amazon shopping applications. If you go take a look at your Amazon web app and you go into the camera settings, you would be able to find a similar feature, which is searching for images. So let me try to explain to you how visual search actually works from the machine learning perspective. So first of all, there is a concept which I want to convey. It's something called embedding. So the idea is that there are, as you pass your images through a neural net, what you're really doing is you are looking at taking a hash or embeddings. So I'm actually back to the first example here we're looking at. So the embeddings are essentially this particular neural net layer. So in essence is that as we take an image and pass it through the neural net, it's able to summarize it and give it a signature through this array of numbers. So this array of numbers is something what we call as embedding. So think about it, it's like a signature or a hash of your image. So if you pass all of your images in a search set through that the same convolutional neural net, you essentially have these embeddings that you can look at the distances between them and figure out how far away or close they are. So in a simple terms is that how similar or different these images are, right? So that's really how it works. Let me go back to the slides. So the way it works for image search for product catalogs or facial recognition. So all of these are essentially using the same methodology, which is essentially running all your images. You train your neural net first with a convolutional neural net, and then what you do is you take the last layer and take that number and start cluster them together and do some comparisons between them. And then you can, as you have new images coming in, you can run it through the convolutional neural net, get a hash. So that is the, I would say, the pipeline stage. So first of all, you would run your image normalization and augmentation, and then you will do your embedding. So essentially passing all your images through the neural net. And then finally, you'll use k-nearest neighbor, which is a clustering algorithm, and plus ranking. So then you can essentially look at the images yourself. So what we do have here is there's a lot of different domains you can apply this to. So you can look at landmarks, retail, adult images, which is actually used quite a bit in terms of in terms of filtering out the right kind of content. And of course, there's other fields that you can apply this to. So another concept I like to introduce here is something called dimensionality reduction. What that means is that when you look at all these different images, these are essentially calculated in the dimensionalities of the number of pixels that you have. So these are very complex systems where you are, mapping out. You're mapping out, fairly complex, I would say, data sets. So first of all, let's actually look at another example. So this is actually a demo that you can run yourself as well. It's called projector.tensorflow.org. What you can do is you can go to MNIST dataset. And let me continue to help you understand how embedding works. So first of all, the dimensionalities of these images are 784. I think they're 28 by 28 pixels. So essentially, these are handwritten digits. And if you think about data complexity, one dimension is, we can visualize that. That's just a line. And if you have two dimensions, that's a plane, right? So if it's three dimensions, that's a space. 784, it's really going to be very hard for us to be able to visualize. So instead, what we're doing is that we're using something called TSNE, which is a way of looking at dimensionality reduction. So you're essentially looking at still three dimensions that humans are still able to visualize, but you're looking at the most important three dimensions of this data set. So this gives you a very good idea of what the embeddings look like as you reduce dimensionality and you can visualize it. So what I'm doing here is I'm actually running the algorithm on it right now. So we're not running the complete algorithm on 784 dimensions, but instead what we're doing is that we are looking at it from the perspective of Yeah, we're looking at it from the perspectives of taking the three most important dimensions and try to look at where they land in terms of the distances between them. So in essence, if this algorithm were to work correctly, the ones would actually be all clustered in a very similar space, while the twos are close together in another space. And of course, the three and fours, they're all kind of clustered in their own space because the embeddings would be similar, or the signatures of these images would be very similar to look at. So as you can see that as we iterate through this algorithm, we're already seeing that they're being clustered together in a very similar way. So dimensionality reduction is part of the data science process, which you're doing the data exploration before you actually run the algorithm necessarily to do a the full-blown algorithm. To visually look at, inspect what your data set roughly looks like. Okay, as you can see that I can, just by looking at three of the dimensions out of the 784, I can see these images being kind of grouped together already. Of course, if you add more dimensions to your system, the accuracy would be a lot better. But in essence, by looking only at three of them, you're still able to do quite a bit. Okay, let's move on to the next slide. Okay, great. So another interesting scenario which I would like to go into is something that I recently started playing with. It's something called generative adversary networks. So the idea is that you have two networks. So first of all, we want to generate images or generate images that are more or less accepted or that is indistinguishable from real ones by asking the system to generate these from a data set by adding random noises. These are not exactly the same images from the data set, but these are images that are similar that it's actually generating. So the way GAN works is that it has two parts. One is something called a generative model, which continuously adding noises to these images. So it's actually generating a random image. And then there's another part of the system, something called discriminative model. So the idea is that the discriminative model would look at the generated image and say, hey, this one does not look quite like it's correct. And then you essentially feedback, take the feedback and send it back into the generative model until two models can no longer tell the differences. So they become, so for example, the images that are generated that are so good that the discriminators can no longer tell the difference. So what's so interesting about this? So there's a recent paper by NVIDIA that is called Progressive GAN. So the idea is that you can generate celebrity faces that are not actual real persons. But we applied the same technology to a data set that I got from Amazon.com side. It's a company called Shop Bop. So we took about 30,000 of these shoe images, and we want to see if we can actually generate images that are indistinguishable from actual shoes. So here's what we actually did. Scott, could you please play the video? Great. So as you can see from the video image, so these are actual shoes, or these are actually, well, I would call it them fake shoes that we designs that we've generated using this progressive GAN technology. So the training itself took about 2 days and 5 hours to do. So essentially the way it works is that we start with 4x4 pixels, and then we increase that to 8x8 and 16x16 until we hit about, I think it's 128 by 128 pixels. So as we progressively train the model becomes very good at generating images of shoes that are essentially indistinguishable. So the retail fashion business is a $2 trillion industry by 2025. So there's a lot of waste in terms of inventories and among other things. For example, if you designed shoes that you've already sent them to factory, but you are not able to sell them. Or maybe there are customers that are really looking for a specific type of shoes that they would like to be made custom using 3D printing. So there's a lot of interesting things you can do using this technology to be, I would say, AI assisted design to be able to reduce a lot of waste and also give a much better customer experience. So there's a lot of interesting scenarios that these machine vision algorithm can do for you. So the next, I would like to change subject a little bit and talk more about the type of hardware, the actual EC2 P3 and P3DN instances. So first of all, these are essentially the Volta 100 GPUs that NVIDIA has released. The latest one that we released, the P3DN, is the 32 gigabit version with 100 gigabyte networking that's interconnected with all of them, all the different nodes. On each of these hosts, we have up to 8 NVIDIA Tesla V100 GPUs with NVLink. So I think we're the only cloud provider that currently has that available. There are also a lot of customers that are starting to take advantage of it. So the ones I want to call out is Airbnb as well as Toyota Research. So there's a lot of interesting use cases. More traditionally, these GPU instances are actually used for high performance computing. The reason it was so efficient at doing high performance computing is because it's very fast at doing matrix calculations. So if you think about convolutional neural net, there's a lot of steps of the convolutional neural net. It's actually running the filters through the images. If you think about how filters work in graphics, they're essentially doing matrix multiplications, right? So you have two matrices that multiply against each other, and each of these GPUs have thousands. So in this particular case, the P3 instances have 5,120 cores. So each of these GPUs have 5,000 cores that are streaming processors that are able to do matrix multiplication in parallel. So if you think about, there are 8 of these per node, and then you can scale that out further with the 100 gig interconnect. So you can do a lot of these trainings very efficiently. So essentially you're doing millions or I would say billions and billions of even trillions of calculations in terms of matrix multiplication. And then here's some more details. If you log onto your console, you will be able to see that the P3 2X, which gives you 1 GPU, up to P3 16 as of before reInvent. But now, if you look at the new offering, we have the P3DN 24X large, which are essentially 32 gig GPUs with NVLink. So you also notice that the number of CPU cores have increased to 96 with the new CPU type Skylake. So we actually had customers asking me about not having enough memory on these instances in the previous version. So the new version has 768 gigabytes of RAM, and the network bandwidth has also increased dramatically. So if you have a lot of data that you need to move, it's certainly going to be able to help. And finally, that the local instance storage has a 2 terabyte NVMe SSDs connected to them. So in essence, you would be able to really cache a lot of data onto each of the nodes, really feed those hungry GPUs efficiently. And the other interesting thing that we are doing is that we have a new team that is actually building very efficient TensorFlow libraries that's optimized for these type of instances. So we're able to take the stock instances of 65% efficiencies all the way up to 90% to fully utilize these type of hardware. So here's another example, and one example is that we ran the ResNet 50. ResNet 50 is one of the convolutional neural net that people have built, so there's ResNet 18, ResNet 50, and there's ResNet 150, 52. It just depends on how many layers there are. The more layers you have, typically, the more accurate these models would be. As you can see, these training typically would have taken you days to do, and you can do that in less than an hour using 8 P316 extra large instances. So there's also some benchmarks that which you can take a look at. I haven't seen any of the new benchmarks with the P324 N instances, but you should be able to see even better improvement in the coming days. So Toyota Research is actually using our P3 instances to run their research training for self-driving vehicles. So these include a lot of the object detection type of models that you saw earlier. So there is a significant improvement and advantage in using the EC2 P3 instances, especially when you have very large models like Toyota Research has. So and the next step is that I'm going to actually do a P3 instance demo. So first of all, if you were to go into your AWS console, you should be able to find your EC2 very easily. I have it set up. Recently, I have used it, so I just picked it out of the instance. So the way to create a P3 instance is really simple. You go to the instances, and you launch an instance. We also have deep learning armies. So you would want to pick deep learning. You can just simply type the deep learning in the search box, and you'll be able to find the 5 latest deep learning AMI, Amazon Machine Image. I would recommend using the Ubuntu Deep Learning AMI, and we update them very frequently. So they also contain the latest drivers for Intel as well as the NVIDIA GPUs. And if you have any type of request, we'll be very happy to add them. So I think we, in the last 6 months, we added things like Chainer, among other packages that people wanted. By the way, there's also a Windows Server version. So I actually do have a few customers that are interested in using the Windows Deep Learning AMI. It also comes with TensorFlow, Caffe, and MXNet. If you like to use that as well. So the next step is that you can select one of these and then go into the instance type and pick a GPU instances. You'll see that we have a lot of different type of instances. So first of all, the G2s are really meant for graphics. They're workstation class GPUs. They're not meant for doing machine learning type of activities. The P2s are a lot less expensive. And then you can if you are just starting to learn about deep learning, I would suggest these are going to be a good choice for you because they're less expensive. Of course, there's the P3s, the P3 instances. They typically cost about $3 an hour or so, and going all the way to our latest and most exciting instances, which is the P3DN 24x large. And they also come with SSD. So if you have a lot of I/O that needs to happen on each of these nodes, the GPU instances will be great for them. So for myself, I've already launched a couple of instances. So I essentially just connected to them. So what I'm going to show you is that you would SSH into these deep learning army, and then the next step is to just start Jupyter Notebook. So if you want to run any kind of deep learning models, Jupyter is probably one of the most popular development environment for machine learning and data science. So you can simply just type Jupyter Notebook. As you can see, by default, you'll get MXNet P336 installed. And if you want to, use other environments, so it's all the environment is configured with Anaconda. You can use CNTK, which is a Microsoft product, PyTorch, Facebook built that, TensorFlow, as well as Theano and Caffe and Chainer. So all of these environments are actually already built for you. So you can pick any of them by just simply use source activate. So this is no different than Anaconda that you would normally use, except for we have a lot of drivers that are optimized for these instances, especially in the distributed computing setting. And I already have a couple of notebooks running. So if you run that, you're going to go to the browser. So I'm actually running this remotely through the SSH connect. So one of the things I do want to show you is that when you SSH into a machine and you want to set up the ports properly for Jupyter Notebook, you might want to use something along the lines of SSH-I your key, and then you're port forwarding your port 8888 to your local port 888 using Ubuntu. So that way you can actually run this notebook remotely against essentially in your local host that's SSH tunneled over to the P3 instance. So in this particular case, I'm actually running something called a transfer, running a model called transfer through transfer learning. So the idea is that I would take a pre-trained model like the ResNet. You'll be able to find these models that are pre-built everywhere. ResNet is just a very common one. You'll find MobileNet among other ones. And so in this particular case, instead of doing a ResNet 18, I'm using MXNet. I'm using MXNet as very raw way of using it. So the first thing you would do a transfer learning is that you would download the actual model. So you would download the model from the system. So it consists of two files. One is a parameter file, which has all the weights of your model. Essentially, this is billions of parameters. And then there's this JSON file that describes the architecture. It shows you what those 152 layers are. And then finally, we have set up the model to essentially say, okay, I want to remove the last layer of that model. So instead of running a classifier for 1,000 different image classes, I will remove that last layer. So in here, I'll remove the original 1,000 layer, and I will keep the original weights, and then add 196 dimensions. So it's almost like my kids learning how to recognize images. So they would look at a horse, and they'll say, oh, that's a horse. Then when they see a donkey, they might say, well, that's a horse, right? So, but they know at least what, they get very close. But instead what we're doing is we're taking the trained model and say, hey, I'm going to ask you to remember what you already learned, but instead I'm going to ask you to learn something new. So we're going to keep what you learned, and I'm just going to add that last layer and have you learn that. So the training process typically takes a while. So in this particular process, we're actually, let me actually just run this particular notebook. You have to tell it, how many times I want to run through the number of images that I have. So in this particular case, I'm actually running that through a set of cars. I gave it a data set, and the data set is all pre-labeled. at the end of the day, and I asked asked the system, say, hey, I want to know what kind of vehicle this is. So in this particular case, I already trained my model, and it's looking at this particular image. It's it gives a not very confident. In fact, actually, it's identifying it wrong. The reason is because I didn't train my models for too many times. If I start adding that to, number of epochs or the number of times that I trained through the data sets, 200 times instead of 20, it would be able to do that a lot more accurately. So let's actually find out. So now it's actually able to tell that this is a BMW 3, and I think that's correct, instead of a Rolls-Royce. So as you can see, the more number of iterations you actually train your model, the better it will actually become. So now let's actually go back and train the models so that I can show you how the GPUs are actually running. So I'm actually having this running. So what I'm going to do here is I'm going to come over here and have you look at the monitoring. So this is essentially running something called NVIDIA SMI. As you can see that it's not currently running very much. It's running at 25 watts, and it's the temperature is ambient, and it's not doing much. But let me actually just run this again, restart, clean out, and I want to go ahead and run the all the cells, run all. So now it's actually restarting the models and running that in the GPU. Let's actually take a look at this to see if it's able to process it. Okay, let me run it again. Now you can see it. So there's a little bit of delay there. As you can see, that now that I'm running the training model, it's taking the Tesla GPU all the way from 38 Celsius up to 62 Celsius, and it's instead of using 25 watts of power, it's utilizing almost a 91% GPU utilization and 220 watts or 230 watts. As you can see, it's running this particular environment. It's running the Python Anaconda environment. And another interesting thing to see is that the amount of memory it's utilizing. So when you do the training, it's very important to keep the GPU memory occupied so that you get the best performance and efficiency for these. So let's go to the next part of our presentation, which is SageMaker. So we talked about how you could potentially run everything inside just a P3 instance. But there's a caveat to that. So there's a lot of people that I've talked to and I've worked with. They all have one problem, which is they forget to turn off their P3 instances. And that becomes expensive. And sometimes your manager become upset. That's because you just run idle computing. In fact, I actually had quite a few people that come to me that said that becomes a problem. And having everybody SSHing into an individual instance, not having that shared becomes also relatively wasteful. So there is a new Amazon service called Amazon SageMaker. Essentially, it's a fully managed service that allows you to do machine learning that includes three parts. One is the notebook service, which is Jupyter Notebook. You can create a notebook service and do your development in that environment. And then you have a separate training service. You can certainly do the training inside that notebook instance, but you have a separate training service which you can submit a job to a training service that is billed by the seconds. So the idea is that when you are constantly doing training in a way that they might be relatively short runs, but not necessarily going to utilize a machine 100% for a full day. this would actually be the most ideal situation. So since it's only billed by the second. The other advantage of this is that it has a way of distributing the training. So for example, MXNet, we have built-in APIs that allows you to do distributed training automatically. We also have HPO, or hyperparameter tuning, that gives you the most efficient model parameters. And finally, we allow you to have a way of deploying an endpoint inference. So instead of sharing your notebooks to everyone, what you can do is you can host your machine learning algorithm in an endpoint where people can just make a REST call. So in many ways, this is actually a great way of doing DevOps for machine learning. So we also have a lot of customers that are starting to use this. Intuit is one of them. In fact, I think a lot of their teams are starting to use that as a collaboration tool. And in the future, I'll be very happy to do another session that goes into the details of SageMaker, what it's capable of doing. But today we have about another 5 minutes to take a look at what the environment looks like, and perhaps you can also try it out. As I said earlier, SageMaker is consisted of the notebook instance where you can host your notebooks in there and run the machine learning algorithms that are either built in. We have an array of machine learning algorithms that includes some of the traditional ones like XGBoost or price forecasting, as well as image classification and object detection. So we have a lot of these built in, and then we also have ML, the ML training service, which are automatically distributed and billed by the seconds. And finally, there's the ML hosting service, which allows you to open an endpoint through the SDK so that people can run it through. Let me run the SageMaker demo. So first of all, you can also follow along by going to the URL, this particular URL. So this particular URL has two labs. One is the object classification, as we mentioned earlier. Essentially, you're doing image classification. You're classifying a large number of images, and then we also have the object detection, which is essentially finding bounding boxes throughout the scene and detecting objects that are in that scene. And then we'll actually run the demo real quick. So if you go into SageMaker, you'll be able to see that Amazon SageMaker has a lot of great new features that just got published. One is the ground truth that allows you to do labeling for your data sets, which can be difficult for a lot of people. As I mentioned earlier, the revolution of machine vision, part of it is because the amounts of data that we have available to us has gotten to a few orders of magnitude, thanks for a lot of the researchers who have done that. So if you were to do the same, you're going to need a lot of data. So in fact, if you were to do image classification, I recently did a project. We basically throw away any classes that has less than 1,000 images. So you really need a lot of images to be able to do these properly. So, and here's the notebook instances. As you can see, I have quite a few of them. I have one of them running, which I'll go into in a second. And also there's the training jobs. Training jobs are essentially ways of submitting jobs that can be trained. As you can see that I did a few training jobs recently. So some of them took 10 minutes, some of them took 20 minutes. I'm only billed by the seconds. And then there's the hyperparameter tuning, which lets you find the best hyperparameters for your model. And then inference. Inference is really the way of hosting your machine learning models. So we also have some interesting new technology called elastic inference models that allows you to rent a fraction of a GPU to be able to do inference rather than renting an entire one. So that would allow you to very economically host these models, especially for machine vision, where you're essentially using a lot of the graphics capabilities or the matrix multiplication capabilities of these GPUs. So let me look at, let's actually look at SageMaker examples. So if you launch one of these, by default, you're going to see a bunch of SageMaker examples. We're not going into a lot of details, but instead what we're going to look at is one of the labs that we are doing. So this is more or less doing the same thing as I showed you earlier. So this particular example is running image classification through 256 classes using the SageMaker API. So as you can see, it's actually very, very much simplified when it comes to running these models. So in essence, the trainings and the models, all you're really doing is running the estimator. So you're telling it what kind of machines I want to train this with. What's the volume size? Where's the file? What's the maximum runtime? And I have hyperparameters. So before I had to write a lot of code for doing this. So in essence, for these built-in algorithms, we have wrapped everything for you so that you just have to specify a number of layers rather than having to download the models, copy them over, reloading them, remove the last layers. Here you just say one. Hey, I want to use this as a transfer learning, which is I want to instead of training from scratch, I want to just use the pre-trained model plus whatever that you're going to train me with these images. And those are all that hundreds of lines of code has been just basically kind of simplified down to just these two sections of code. And then you're just basically running the training. So in this case, I actually submitted a job to run on this on the remote system. So in this case, I'm using a P3 2x large instance to do the training. As you can see, the training took a little while, took about 6 minutes to complete. And the next step is that I actually deployed an inference endpoint, asking SageMaker to give me a place where I want to host the model that I just trained. And then finally, I want to be able to call this particular endpoint and actually figure out what this image is all about. So in this case, I'm looking at a bathtub, and the code basically tells me that I have a probability of 98% or 99% that this is a bathtub, right? So the classifier essentially is running correctly. As you can see, this is much simpler if you use one of the built-in algorithms of SageMaker instead of having to write a lot of this on your own. And finally, I want to kind of talk about where to go from here. So we talked about deep learning today. So deep learning is really revolutionizing the world of machine learning because of the fact that they are much more accurate. The caveat is you need a few orders more magnitude amounts of data. So you need the more data you have, the more accurate these deep learning algorithms will become. So in essence, these deep learning algorithms are able to capture much more complex models of these data sets that traditional machine learning algorithms are not able to with lots of data. However, it doesn't mean the traditional machine learning algorithms are obsolete. They are still great if you have small amounts of data. So a lot of people don't have a lot of data, then you do just fine with them. So there are other topics I will go into more details in future broadcast. One is autoencoders. These are other machine learning algorithms that are very interesting. Autoencoders that lets you do anomaly detections. RNNs are essentially time series data set. Time series algorithm that they're also very, very good at translation among other natural language processing things. And then another topic is also very interesting, is called inference. So how do you deploy your models onto your cell phones? How do you deploy your models onto let's say edge devices like the NVIDIA TX2 that has a little GPU built in for a $200 embedded chip. And also, there's other topics including, how does elastic inference work? And finally, we'll be also very happy to discuss things like DPLANs. DPLANs is a little camera that has a little bit of Intel GPU built in that the AWS published recently. And of course, I really want everyone to look at the new book that MXNet and also the Amazon Machine Learning team has published. It's called Dive into deeplearning.org. So what I will do is I will actually go into the website a little bit. Yeah, so this is actually the book. So we'll go into the basics of deep learning, which we had to very quickly cover today. So if you're interested in knowing the math behind it and how it really works, there's convolutional neural net, there's recurrent neural net, optimization on algorithms, computer vision, natural language processing, which is one of my favorite topics, and I cover a lot of the interesting, I would say, all the basics and the interesting the development in the field. So I would strongly recommend that you get this book. And this book is not just a PDF; it also consists of Jupyter notebooks, which has all the examples you can run from the P3 instances yourself. And for those of you who speak Chinese, there's a Chinese version for it as well. And for that, I would like to conclude this broadcast, and I want to thank everybody for attending. And if you have any questions, I'll be happy to try to answer them with the time that we have left.